Hello, and in this first video in a series about the bandwidth of op-amp amplifiers, I just want to go over what topics we'll be covering in these videos and a few basic concepts, just a quick revision of things that we've seen before that are going to be relevant. So in terms of what we'll be covering, we'll be looking at definitions of bandwidth and how to represent a real op-amp's behaviour in terms of a dependent source model. We'll be looking again at some of the formulas that we produced for that circuit where there was a voltage source driving a capacitor through a resistor, because those equations are going to be very similar to the equations that we're going to come across in our analysis of op-amps as well. We'll then derive some formulas for the bandwidth of a inverting, a non-inverting, summing and differential amplifiers, and finish off by deriving a useful formula for determining the x dB bandwidth from the 3 dB bandwidth. We'll start by having a quick look at a simulation. This is a standard non-inverting configuration with a gain of 10. We're putting in a 1 volt sine wave and we're getting out, as expected, a 10 volt sine wave. The phase difference between the output and the input is 0. Plotting the gain on our usual scales with the dBs on the y-axis and the log of frequency on the x-axis results in a straight line. And that is exactly what an ideal op-amp would do, because an ideal op-amp has a practically infinite open loop gain, and that open loop gain is not a function of frequency. However, if we replace this ideal op-amp with a real op-amp, then the graph gets a bit more interesting. As you can see, the gain is now not constant with frequency. It starts off about 20 dBs, and then starts to drop at higher frequencies. And if we moved up to higher frequencies still, it would just keep dropping. The phase changes as well. As we start to move to higher frequencies, the output is no longer at the same phase as the input. There is a phase difference between them. And you can see that by looking on the phasor diagram here, seeing that the output phasor is no longer horizontal. It's no longer along the real axis. Since we have a gain now, which starts at a high level and decreases with frequency, we can start to define the bandwidth of this amplifier. And as a reminder, the bandwidth is the range of frequencies within a certain factor of the maximum gain. And there are many different bandwidths that can be quoted for these circuits. The 3 dB bandwidth is the range of frequencies for which the amplifier has a gain within 3 dB of its maximum. In this graph here, the maximum is 0 dB, so the 3 dB bandwidth is the range of frequencies for which the gain is within 0 to minus 3 dBs. But equally well, there are 6 dB bandwidths, 10 dB bandwidths, 1 dB bandwidths, or anything you like. And while the 3 dB bandwidth is the most common, we'll be looking at a few others later on. Now, you may be wondering why it is the 3 dB bandwidth which is the most commonly quoted one. What's so special about 3 in this case? Well, the answer is because it's very easy to determine the 3 dB bandwidth from the frequency response in a lot of simple cases. We've looked at this circuit before. Just a voltage source here, which feeds into a capacitor through a resistor. And if that is our output voltage there, and this is our input voltage here, then we've determined the frequency response before. That's just V out over V in, both expressed as phasors. And we can use the potential divider equation to get an expression for this frequency response. We get 1 over 1 plus j omega RC. And we can express that as 1 over 1 plus j omega over omega b. It's like a standard way of writing it. omega B in this case is equal to 1 over RC. And it's a characteristic frequency of this circuit. We can also write this in terms of the frequency in hertz rather than the angular frequency in radians per second by just noting that the ratio of the two angular frequencies is equal to the ratio of the two frequencies in hertz. Or, to draw that out a little more clearly perhaps, since omega is 2 pi times f, I could replace that omega with 2 pi f, and this omega b with 2 pi fb, where this is the same frequency only in hertz rather than radians per second. Note that the 2 pi's cancel and get the frequency response as a function of f in hertz in this form. And as we've seen before, if you plot this on a graph of dBs on the y-axis and the log of frequency on the x-axis, then at both low frequencies and high frequencies, we get an approximate straight line. If we extrapolate those two straight lines, then the point where they meet is called the break frequency, or sometimes the corner frequency. And it happens that when you can express the frequency response in this form, this break frequency is the 3 dB bandwidth. So we can instantly tell the 3 dB bandwidth as soon as we've got the frequency response in this form. To show that, I have to admit that we're not actually calculating the 3 dB bandwidth. We're just calculating something that's very, very close to the 3 dB bandwidth, so close that engineers don't usually worry about the difference, and we just call it the 3 dB bandwidth anyway. But strictly speaking, it's not. It's just slightly different from the 3 dB bandwidth. What we're actually calculating is the frequency at which the gain has dropped by a factor of √2. Now, the maximum gain, in this case here, I can express the magnitude of the frequency response, which is the magnitude of the gain, just by taking the magnitude of this term here, and that would give me 1 over the square root of 1 plus f over fb all squared. That's just applying Pythagoras' theorem to the term 1 plus j f over fb. If we think about where that is on the Argand diagram, it has a real part of 1 and an imaginary part of f over fb. So the magnitude, which is the length of the line from the origin to this point here, 1 plus j f over fb, would just be given by Pythagoras' theorem, the length of the hypotenuse in this right-angled triangle. Now, this gain has dropped by a factor of √2 when h of omega modulus is h of 0 modulus divided by √2, because the maximum value occurs when f is 0. And h of 0, this maximum value at 0 Hertz, or DC, is just 1. If I put f equals 0 in this formula here, I would just get 1. So that is just 1 over √2 in this case. So, what frequency gives you this as the magnitude of the gain? Well, that would just occur when 1 over the square root of 1 plus f over fb squared is equal to 1 over √2. And by examining that formula, it's hopefully fairly clear that 1 plus f over fb all squared must be equal to 2. In other words, f over fb squared must be equal to 1. Take the square root of both sides, we just get f over fb must be equal to 1. In other words, f equals fb. That's the frequency at which the gain has dropped by a factor of √2. Now, if I expressed this amplitude drop by a factor of √2 in terms of dB, I would get this. 20 times the log of 1 over the square root of 2. It's not quite minus 3 dBs, but it's very, very close. And as I commented before, I think engineers don't usually worry about the difference. And we just call it the 3 dB bandwidth. It's almost the 3 dB bandwidth, but not quite. That's all I wanted to say this time. Next time, we'll have a look at developing a model of a real op-amp based on the concept of dependent sources.